The next reaction we're going to take a look at in terms of addition to pi bonds is called the oxymercuration reaction. It sounds kind of ominous, but essentially you're going to take an alkene and you treat it with mercury acetate in water followed by sodium borohydride. Now these reagents are relatively new. I'll talk about them in just a little bit, but the result is that you make an alcohol, right? So this is another way of making alcohols. Now, when I take a look at the reagents, mercury acetate, OAC, OAC is acetate. It's an abbreviation for acetate. You haven't seen it before. You may have seen it before, but I'm certainly going to highlight it here. Acetate ion looks like this, so simply be familiar with that and recognizing that when we draw HgOAC, that's simply mercury 2 acetate. Now NaBH4 is called sodium borohydride. Borohydride, the structure of a borohydride, we've talked about boranes, but we haven't really talked about borohydrides, looks like this. So boron has 4 hydrogens around it. It's tetrahedral. It has a negative charge on it. Now the thing about borohydrides is the name implies is a hydride agent. So borohydrides often can donate hydride, H minus, H with 2 electrons, so that you get borane back, right, once you've donated a hydride. And we'll see how that plays out in a little bit, okay? Now, in terms of the mechanism of oxymercuration, how do you make an alcohol from mercury acetate and sodium borohydride? Well, let's take a look at the first step. I take an alkene and I react it with mercury acetate. So here's mercury acetate. Mercury has a lone pair of electrons on it, non-bonding pair of electrons, and then it has 2 acetate ions coming off of it. And what happens is the pi bond, so mercury is a Lewis acid. A lot of metals are Lewis acids, so it can accept a lot of electrons around it, and certainly it can accept a pair of pi electrons. Now when it does so, it can donate a pair of electrons back to the alkene, and you break a mercury acetate, mercury oxygen bond from the acetate. The result is another cyclic intermediate, right, a 3-membered ring with mercury that has a positive charge on it now that only has 1 acetate because the other acetate came off. And this is what we refer to as the mercurinium ion, the mercurinium ion. Now, you should be thinking about patterns, right? Similarities. And certainly there is a similarity between this and the formation of the halonium ion, right? The bromonium ion or chloronium ion. Basically, it's a very similar pattern that emerges from this, right? Pi electrons attack the mercury, a non-bonding pair of electrons from mercury go to the pi system of the alkene. And of course now what's going to happen? Well, this is usually run in water. Water's the solvent. So water is now going to attack this mercurinium ion. And it attacks the carbon that's more substituted, just like when we were making halohydrins. So it's going to attack that carbon, and the carbon-mercury bond breaks. And so the result is now I have this intermediate where I have to, I have the oxonium ion with a mercury acetate on there, and so I simply can deprotonate that oxonium ion again with water. I could also use acetate. So oftentimes you might see acetate, the acetate ion being used. And as a matter of fact, that might be a better source because acetate, the conjugate acid of acetate is is acetic acid, which is a weaker acid than the hydronium ion. But here I'm going to, use water because, again, water is the solvent, so there's a whole bunch of water present. So I deprotonate it, and I end up with this species here, where I've added OH on one carbon, and the other carbon still has a mercury attached to it, and of course the hydronium ion is formed as well. So this intermediate here is called an alkyl mercury compound, and actually I can isolate alkyl mercury compounds. They're relatively stable, but they're not very synthetically useful, and so generally speaking, in a subsequent step, I take this mercury alkyl acetate and I react it with sodium borohydride. Now your textbook doesn't talk about the mechanism of this reaction, but I want to kind of go through the mechanism of this because it's kind of a cool mechanism, and it's an introduction to the borohydride reagents, right? Borohydride. Remember I said borohydride is a hydride agent. It supplies hydride. So I can think of borohydride as borane with a hydride attached to it. The boron has a negative charge. And it can donate its electrons and the hydrogen. So it's going to donate a hydride to the mercury. So it's reducing the mercury. And when it does so, that second acetate ion breaks off. And so what I end up with is now an alkyl mercury hydride. Now the alkyl mercury hydride is relatively unstable, and it undergoes a homolytic dissociation. So I'm getting a homolytic dissociation. One electron goes to the carbon, one electron goes to the mercury. The result is that I form a radical. So a radical alkyl radical, and now the mercury has one unpaired electron. So, but the mercury has a hydride attached to it, and so what happens is that the radical, carbon alkyl radical, then will donate its electron with one electron between that hydrogen-mercury bond. The other electron goes to the mercury. So now I'm going to form a carbon-hydrogen bond. And there's my new carbon-hydrogen bond. And I form mercury. So mercury is a liquid. And I actually end up reducing the mercury in this process. So this is an oxymercuration and then followed by a reduction. The sodium borohydride reduces the mercury to mercury metal, mercury liquid, right? And in the process, a hydride is actually transferred to the carbon. All right, so what's kind of the overall reaction here? So if I take one butene and I react it with mercury acetate and water, followed by sodium borohydride reduction. So again, 2 steps. I end up with 2-butanol. And this is a Markovnikov addition, right? Well, remember, if you recall, we've already seen a Markovnikov addition. If I take 1 butene reacted with water and sulfuric acid, I get the same thing. So why would we need another reaction to give us the same product? Well, in this particular example, you probably don't need to, but the key is in understanding that mechanism and forming the mercurinium ion, you do not form a carbocation. And if you do not form a carbocation, you cannot get rearrangements. And that is certainly the key to a lot of these types of reactions, right? So oftentimes we don't want rearrangements to take place. And as a matter of fact, an example of this would simply be if I looked at the reaction of 3-methyl-1-butene with water and sulfuric acid. What's my major product? Well, let's think about what the major product would be. I'd form a carbocation. It's a secondary carbocation. It's connected to a beta carbon that is a tertiary carbon, and so I can undergo a hydride shift there, and that's certainly going to take place to form a more stable tertiary carbocation, such that when water adds, it's going to add to that carbon, and I get a tertiary alcohol. That's not what I wanted. If I simply wanted to add across that double bond, I'd be in for a kind of a rude awakening there. So this is a perfect opportunity to use the oxymercuration, because I can take that alkene, react it with mercury acetate and water, followed by the reductive workup, and I would get the product that I desired, that 3-methyl 2-butanol in the process. Instead of getting 2-methyl 2-butanol, I would get my desired 3-methyl 2-butanol, because I don't have to worry about rearrangement. So that's certainly a key to oxymercuration, followed by that reduction. Now, there are other, I'll call them twists to this particular reaction. Notice, we react the alkene with mercury acetate in water, and water behaves as the nucleophile. I can, instead of using water, use an alcohol. And what do you think I would get in that type of reaction? Well, let's say I used I reacted 3-methyl 1-butene with mercury acetate in, let's say, methanol, followed by that reduction with sodium borohydride. Now I form my mercurinium ion, and methanol is present, so methanol would attack the mercurinium ion, and I would get an ether, a methyl ether. So this is another way that I can make ethers, and again, not have to worry about rearrangements taking place. The other thing that I can do that's kind of a nice little twist on this reaction is, instead of using sodium borohydride, I can use deuterosodium borohydride, NaBd4, so heavy hydrogen in this case. So this is called deuterosodium borohydride. And what happens? Well, notice the hydrogen is adding to the least substituted carbon there. Instead of a hydrogen adding, I would add a deuterium. So for example, if I took 1-methyl cyclohexene and reacted it with mercury acetate and water, followed by that reduction with NaBd4. So instead of a hydrogen adding to that bottom carbon, I would have a deuterium adding to that bottom carbon. So, understanding how each reagent works is certainly key to understanding the product outcome of this reaction. So all these little twists make organic chemistry fun.